Thank you very much. Today I'm going to present my research on comparative analysis of high and low-performing factory workers with attention-based neural networks. Our research focuses on factory workers working in assembly work sites. On these sites, workers are doing repeated works, such as packing boxes on a streamline. However, the skill level among the workers are different, which will influence the factory's productivity. Comparing with the high-performing workers, the low-performing workers perform slower, resulting in a delay in the streamline. Besides, they are more likely to make mistakes during their work. Due to their limitations, it's important to improve the performance of the low performers during the work for the factories. Traditionally, many industrial engineers were employed to manually compare videos and sensor data between the high and low performers to identify skills. Then, this skill will be used to design technical training courses to help the low performers improve their skill fast. However, because the number of workers is large in the factory, manually extracting skill is time-consuming. In this research, we will focus on designing a supporting technique to manually detect the workers' activities that potentially contain skill. And here is an example result actually output by our proposed method. Our method extracts a sensor data segment from the high-performing worker corresponding to an attaching label activity. However, it's difficult to know if this segment contains skill when we only focus on an individual worker's result. So, we also try to find the corresponding attaching label activity on the low-performer workers, and then ask the industrial engineer to check the video at these timings. The engineer noticed that the high-performing worker bent his knees in front of the workplace, while the low-performing worker bent his upper back, resulting in a heavier body load. This is a very helpful skill knowledge for the workers to reduce their fatigue levels. And this is the procedure of how the engineer quickly identifies skill with the help of our approach. And in other words, if we can achieve these two objectives, the work efficiency of industrial engineers to identify skills can be easily improved. However, identifying if a sensor data segment contains skill is challenging. For example, we don't know if the segment 1 or 2 actually contains skill by only looking at the raw sensor data. Besides, the corresponding activities done by different workers have different sensor data, which I will explain it later. Our approach corresponding to the first objective uses a classifier to identify the sensor data patterns that potentially contain skill. There is a worker who repeatedly performs a packing box task, and we collect assertion data from the workers raised. The first idea says that some sensor data segments or patterns frequently occur in each iteration, which is necessary for the target task. In this example, the attaching label appears in every iteration, which is a very necessary action for the packing task, as we need to use the label to record the proceedings of the task. The second idea says that if the pattern is different from the low-performing worker, it has a high probability relating to skill. At the same time, different patterns are helpful to differentiate different workers, which inspires me to design a worker classifier to identify these patterns and then extract useful knowledge from the patterns. Our approach to the second objective is to use an autoencoder to find pairs of segments that are semantically similar. Because only using an individual's work data is difficult to identify skills. So we also need to find the corresponding activities on the other worker and compare with both workers' data to identify if this activity contains skill. However, sensor data between these workers are very different. Our approach leverages an autoencoder to extract semantic features of the segments and eliminate the difference between individuals. This is the overview of our method. The input is time series of every iteration of work for both high and low performing workers. The network is trained to classify high and low performers, where the attention mechanism is used to highlight some timings as candidate segments that potentially contain skill. And for each candidate, we find corresponding activities on the other worker by using the clustering result of the latent representations of the network. The output is the pairwise sensor data segments, which will be sent to the industrial engineers for further skill identification. This is the structure of the network. We use an autoencoder structure to preserve the main component of the input data, and a LSTM-based classifier is trained to classify workers and detect the input sensor data segments that potentially contain skills. We use an autoencoder because we want to maintain the structure of the latent representation. The autoencoder consists of several 1D convolutional layers that extract short-term features of the time series and keep the feature sequence similar to the input. The reconstruction loss of the autoencoder ensures that the 1D convolutional layer preserves the main component of the original data. We connect the latent representations to a worker classifier to identify the sensor data patterns. However, network training is regarded as a black box. This work leverages an attention mechanism that provides information about the importance of each data point in time series, enabling us to find a candidate segment with high attention values that potentially contains skill. Our attention is a time series that is calculated from every LSTM layer. By multiplying it with LSTM features, important timings can be emphasized. On the other hand, we can output the attention values to visualize the importance of input segments. Based on this idea, we select the input segments with high attention values as the candidate segments that potentially contain skill. As for the second objective, after training the network, the latent representations can classify workers, but they still keep high similarity in similar activities. Therefore, I use a clustering method to roughly eliminate the difference between workers so that similar activities still belong to the same cluster. And here I will explain how to find the corresponding segments. Assuming that this is a candidate segment identified by the attention mechanism, then we need to find the corresponding segment on the other worker, because using an individual worker's data is difficult to identify the skill. I first simplify the role sensors into symbols according to the clustering result of the latent representations. Then I calculate the similarity score to find the most similar symbols on the other worker. I also calculate a temporal score to remove the segment that is similar in activities but different in timings. This score is based on the fact that the order of activities in assembly works between workers is similar, and it's more reliable if the occurrence of corresponding activities is similar in timings. And finally, we will offer the pair of segments to the engineer for the skill identification. To evaluate our method, we evaluate it in both qualitatively and quantitatively ways. We calculate the mean square error to evaluate the performance of identifying corresponding segments on the other worker. Besides, as we don't have the ground truth labels for skill information, we asked the industrial engineer to identify if the candidate segments detected by our proposed method actually contain skills. We test two datasets collected in real manufacturing, and their screening and final check tasks, which are very common in real factory settings. To test the performance of finding the corresponding segments on the other worker, I calculate the mean square error of the corresponding segment to the ground truth. The proposed method has the lowest MSE on both datasets. And this experiment explains that the autoencoder can maintain the data structure similar to the input series. We present the latent representation visualized by the PCA, and different colors shows the different clustering result. The left figure is output by the proposed network structure, where similar activities between two workers are clustered to same set. In contrast, when we broke the decoder structure, the latent representations that belonged to similar activities but different workers were located differently. Because it's difficult to get the ground truth labels for identifying segments that potentially contain skill, so we asked industrial engineers to assess if candidate segments that detected by attentions actually include skill knowledge. The left side lists the candidate segments detected by our proposed method, and the knowledge refers to the skill were identified from the industrial engineers. The result shows that 7 out of 9 candidate segments include useful knowledge. Here are 2 example segments containing useful skill that detected by our method. The left figure shows that modifying the activity order can improve the work efficiency, and the right figure implies that different gestures lead to different body loads. The high-performing worker has a lower movement on the waist so that he has less back pain during the work. This is a very useful skill knowledge that can reduce the fatigue of the workers. However, there are some drawbacks of our method. For example, our method cannot detect the one-meaning actions. In this case, the different ways of holding the measuring tool is an important skill, but we didn't detect it, as the movement of the wrist is very small. In conclusion, we designed an attention-based neural network to automatically extract candidate segments that potentially contain skill, which is helpful for the industrial engineer to identify skill from workers' data more efficiently. Thank you for your attention.